My guest today is Professor Wendy Freedman, who's Professor of Astronomy and Astrophysics at the University of Chicago. Her current projects involve measurements of the Hubble Constant, the current expansion rate, as well as the past expansion rate, providing constraints on the acceleration of the universe and dark energy. Welcome, Wendy.
Thank you. It's nice to be here.
Yeah, thanks for doing this. So we talked a few months ago, and as I mentioned, I was hoping for some data that will show all of our understanding that the lambda CDM is completely incorrect. So we have to start over again, but that doesn't seem to be the case. So you have a recent paper answering the most important problem in cosmology today. Is the tension in the Hubble constant real? You say measurements of the Hubble constant are on the cusp of heralding in a fundamental discovery in cosmology that goes beyond the standard lambda CDM model. Yet published differences in the local distance scale may be indicating that systematic errors, which have long been the bane of the extragalactic distance scale, are larger than currently estimated. So before we go into the details of this, Wendy, I obviously don't have a background in astrophysics, so I'm trying to understand this. So the Hubble constant, a discovery of Edwin Hubble in the early 20s, it's really if I understand this correctly, Wendy, if you plot distance on the x-axis, distance of stars and galaxies from us, and its velocity on the y-axis, so kilometers per second velocity on the y-axis, distance in megaparseconds or millions of light years on the x-axis, you see this relationship between things that appear to be moving faster when they're away from us, right? And so I have two concept questions. I obviously don't understand this. The first question is there a physical reason why this relationship is linear? Couldn't that be exponential or logarithmic or something?
Yeah, the fact that it is linear is a manifestation of the fact that the expansion is uniform and fits in with what is expected from general relativity. If you have a uniform expansion in the universe, then you would see at least nearby this uniform expansion. Of course, the linear relationship only holds nearby because as you go more distant, then other effects, the density of matter and the density of cosmological constant, the dark energy density, come into play, and general relativistic effects. So but it is a consequence of the fact that we're seeing a uniform expansion. So if we are sitting in our Milky Way galaxy and we're measuring velocities and distances of galaxies nearby, we see this proportionality. The farther away a galaxy is, the faster it's moving away from us. But if we were to go to another galaxy and measure around that galaxy, we would see exactly the same thing.
Yeah, that's disappointing. This almost would have proved that we are at the center of the universe, but that's not the case.
No, we would see the same thing at any point in the universe. Locally, we would measure the same effect.
Right. So the idea that things more away from us, are moving faster, is that in itself proof that the universe is expanding? The reason I'm asking is, suppose the universe is closed rather than flat. Would we see some effects that are, that might not really prove that things are expanding?
Well, the fact that the universe is expanding is one piece of evidence for the expansion. Of course, you could have had a steady state universe, which was proposed many decades ago, and you'd have a continual formation of new matter as the universe is expanding. But the fact that we do see the remnant radiation from a Big Bang explosion is the other piece of evidence, in addition to the abundances of light elements that also provide evidence for the Big Bang theory of the universe. But the galaxies themselves are not actually moving through space. We're seeing the expansion of space. That's what general relativity tells us. It's the stretching, essentially, and the galaxies are moving appear to be moving away with the expansion of space.
Yeah, so the stretching of space-time. So we could actually see, if you really sort of measure relative velocities, we could see these things moving faster than light, right?
That's correct. So special relativity tells us that no information can travel faster than the speed of light. So light doesn't, so we can't get information from anything. But there's no speed limit to the universe. So there are parts of the universe that would appear to be moving faster than the speed of light.
And so if our current understanding is correct, it will continue to expand at a faster rate, right? We will see things sort of moving away from us. Do we have a horizon, sort of a time horizon at which we won't be able to see anything anymore? When does that happen?
Yeah, so you're talking about two effects, right? So the fact that the universe is expanding, we can see more and more of the universe as time goes on because there's time for light from more distant objects to reach us. But the fact that, so Edwin Hubble, of course, discovered that the universe was expanding in 1929, but it wasn't until a couple of decades ago that the discovery was made that not only is the universe expanding, but it's actually accelerating in its expansion. So there will things that will recede out of our horizon, and given long enough time, and we're talking 60 billion years or so, but we won't see anything except for the nearest galaxies that are gravitationally bound to us in the local group, say. But the night sky will be very different in 60 billion years. Because things will have receded away from us. Yeah.
In a few billion years. So if humanity were to be restarted at that point, our theories would be quite different, I would imagine.
Yes, well.
Because we can't take any measurements of anything, right?
Yeah, well, the stars in the Milky Way will be bound to us. Wait long enough, dark energy will. But we would see the night sky still filled with stars. But our understanding of the greater universe and galaxies within it will be very different.
So the Hubble constant, H naught, there has been, you spent many decades around measuring the Hubble constant. So what was sort of our first attempt at doing this? So I know that there are multiple methodologies that have been tried. Was it the CMB was sort of the first one, or the Cepheid variables was the first attempt?
Well, the Cepheids, of course, go way back. In fact, Edwin Hubble used Cepheid variables when he first discovered the expansion. He only had a handful of galaxies that he could measure Cepheids in. The telescopes at that point, he couldn't see much farther, so he used bright stars and what came to be known as H2 regions to make his famous diagram. And so Cepheids have been used now for almost 100 years. The CMB measurements, of course, are much newer than that. But what had happened was that based on the Cepheid measurements, Hubble first measured a value of the Hubble constant of 500 kilometers per second per megaparsec in the diagram you were describing. It's the slope of that correlation between velocity and distance. And that value had settled down to about in a range of 50 to 100. And so there was a factor of 2 uncertainty that people were arguing about for decades. And then when the Hubble Space Telescope was launched, I led what was called the Hubble Key Project to use Cepheids measured with the Hubble Space Telescope, get us above the Earth's atmosphere, which allowed us also, with the availability then of CCD detectors, digital detectors, instead of the photographic plates available to Hubble, to measure the Hubble constant much more accurately. So we used Cepheid variables to calibrate 5 different methods, including these type 1a supernovae that we use today to measure the Hubble constant. And we got a value of 73 at that time. And it's remained pretty steady. The Cepheid calibration comes out high. And then the microwave background measurements got better and better in the last couple of decades. And they are so precise in the way that you can measure fluctuations in the temperature and now also the polarization of light from remnant radiation from the Big Bang. And if you assume a model, what we call our standard model now, which provides an exquisite fit to the fluctuations in those temperature and polarization measurements, then you can infer the Hubble constant today. And when you do that, you get a value of 67. So there's this discrepancy between the Cepheids and the coming from the cosmic microwave background observations, which, if it's real, it would imply that there's some fundamental physics that's missing from our standard model. And so the question now is this a real discrepancy, or could there be systematic uncertainties that we haven't yet identified that could explain the difference? And so our group used these red giant branch stars, a method using the tip of the red giant branch, as we call it, to independently calibrate the supernovae, not using Cepheids at all. And we initially expected that either we would agree with the Cepheids or we would agree with the microwave background, and we found ourselves right in the middle. And in fact, there's no discrepancy, statistically speaking, with the microwave background observations. However, it's also in relatively good agreement with the Cepheids. So where I've become really excited is we're about to have the launch of the James Webb Space Telescope in a couple of months now. And that will allow us, we've just been given time on James Webb to measure distances using not just Cepheids or not just tip of the red giant branch, but in the same galaxies, use both those techniques and a third one that we've been developing using a type of star, a carbon star, that will allow us to really get at these questions of systematics. James Webb is bigger, it has more sensitivity, it has better resolution, and we can measure for the first time one of the systematic uncertainties in the Cepheid distance scale has to do with the abundance of the Cepheids themselves. That is, younger Cepheids have been around longer, they're made out of more processed material, so the amount of metals in their atmospheres is higher and affects the luminosity of the star. And that's been one of the big unknowns in the Cepheid distance scale. It's worried us since before the Key project, and the cosmic microwave background observations now, their value of the Hubble constant is measured to a precision of less than 1%, better than 1%, which is extraordinary. And we haven't done that yet with our local measurements because of these kinds of systematic uncertainties. So James Webb is going to let us really get at some of these remaining difficulties. And it remains a really exciting possibility that there's new physics, but we better be sure that we've gotten on top of the systematics. And so that's why I'm really excited about what's coming up. It's a whole new world opened up by James Webb.
Yeah, I want to talk about James Webb in detail, but before we get there, I want to just sort of go back. So the Cepheid measurements, as you say, Hubble had a 5,000 number, and then we went from sort of 50 to 100. As an engineer, I would have just averaged them and say that the answer was 75. And then we made better and better measurements. The variance changed and became less and less. But we sort of staying there, right? As the expectation still from a Cepheid measurements, it's still about 74 or so.
Yeah, 73, 74, that's right.
And then CMB, as you say, we have very precise measurements, but that is coming in at 67. And then what you have been working on for past several years, the red giant, the tip of the red giant branch measurement. So these are things that I guess it's less noisy measurements compared to Cepheid. Is that the way to think about them?
Yeah, I think that's the way to look at them. So these are evolved stars, low mass stars, and the Cepheids are young stars. And so we have no choice but to observe the Cepheids in the disks of spiral galaxies, and they're very close by to the regions where they formed out of gas and dust. And so the bright background of the galaxy itself, they're residing in it. So to measure accurately the photometry, the luminosity of an individual Cepheid against the background, sometimes there are nearby stars that are resolved and crowding it, and sometimes you can't tell what's under the star. It makes it much harder to get accurate photometry when you have to work in the crowded region of a disk. The tip of the red giant branch stars, they're older stars, and we find them in the halos of galaxies. So they're well away from the disk, well away from the gas and dust that cause these systematic effects like reddening and making the stars fainter. And we can tell directly what their abundance is from their luminosity and their color or their temperature. We have no direct way of doing that for the Cepheids. And we can also measure these tip of the red giant branch stars in elliptical galaxies as well as spiral galaxies, and our distant samples have both, and there may be systematic effects there, differences between the two types of galaxies. So for a lot of reasons, the tip of the red giant branch method is just much simpler and less prone, I think, to systematic effects. The Cepheids are complicated. Their histories, their metal abundances, the crowding in the disk.
And so in both of these techniques, the idea is that we can observe luminosity, and given some sort of a heuristic that we can determine from other methods, we can then use that to say how far that particular object is, right? Is that the way to think about it?
So you measure the apparent brightness of the object, and then you have a calibration that is set, and the best way to do that is using a geometric technique for a nearby object like a Cepheid. So you could measure its parallax. So it's most simplest, you can think of it as the Earth is going about the sun. You measure the position of your star at one part in the orbit, and then you say 6 months later, and you can measure that angle. Of course, you measure the entire orbit, but and you can do that. It's high school geometry, right? It's very simple, straightforward to do. And once you have that calibration, then when you measure the luminosity of, say, your Cepheid or your tip of the red giant branch star in another galaxy, you just use the inverse square law of light, and you can determine the distance to your object. But you need that calibration. So, for example, it'd be great if we could use type 1a supernovae without having to worry about Cepheids or tip of the red giant branch at all. But we only know the relative brightnesses of type 1a supernovae. We have to get an absolute calibration of the distance, and the supernovae are just too rare to do that. And we have no way of measuring a parallax for a nearby supernova. So we have to rely on what we refer to as a distance ladder, which has become much simpler since Hubble's time. But nonetheless, we still need to step out into the universe using nearby stars where we have geometric distances, then the realm of the Hubble Space Telescope, where we can measure Cepheids or tip of the red giant branch stars to compare with the geometric calibrations, and then step out to type 1a supernovae. And then we can get out into the distant, what we refer to as the Hubble flow. And the reason we have to go distant is because, again, galaxies are located in groups of galaxies. They tend to interact gravitationally, and so that it adds a noise, a peculiar velocity above and below the Hubble expansion velocity. So as you go farther and farther out, this effect of the peculiar motion is much smaller relative to the Hubble expansion. So it's really a three-step process. And so we work very hard to try and make sure that the calibrations are consistent and that we're comparing apples with apples as we step out into the distant flow. But I think that, again, is we need to be very careful that at each step we are eliminating the systematic errors that could plague us, and that historically, as you quoted before, have been the bane of the extragalactic distance scale.
Yeah, so the basic assumption remains to be these are standard candles. And so we have to assume that the physics underlying them, whether it's a Cepheid variable or a tip of the red giant star, the physics underlying them is standard, and they all do exactly the same, right? Do we have sufficient evidence that's the case?
So I'll distinguish between the tip of the red giant branch and Cepheids again. I mean, the first thing I would say is that, for example, with the period luminosity relation that we use for Cepheids, what we refer to as the Leavitt law. So the brighter a Cepheid is, the slower it's changing in its brightness, the longer its period. And to the extent that we've measured, for example, in the Key project sample, there were a couple of dozen galaxies, and we can measure the slope of the period luminosity relation, and that, to within the uncertainties that we can measure it, appears to be, it's not changing. And we're talking about local physics. We're talking about stars with a particular kind of density. The pulsations are due to the position of their atmosphere, the ionization state of the atmosphere. And that's local physics. You wouldn't expect that that's going to somehow vary by huge amounts when you go to a different location. Where you could have differences, as I mentioned, the abundance of the atmosphere, the metals in the atmosphere could make the luminosities change from metal poor to metal rich galaxies, but that's something you hope to be able to calibrate despite the challenges in doing that. So there's no evidence to within at least the error bars that exist at present that there's some wildly varying difference between the Cepheids from one location to another. And similarly with the red giant branch stars, these are stars that have degenerate helium cores. They have a hydrogen burning shell about that degenerate core, and more matter is being dumped onto the helium core, and the luminosity is increasing as it's burning the hydrogen until the star reaches a temperature of about 100 million degrees. And then there's essentially a thermal runaway. The star can burn the helium in a non-degenerative way, breaks the degeneracy because the temperature keeps rising, and it gives rise to something known as the helium flash, which has been very well studied for many, many decades. And it essentially just depends on the nuclear physics. So again, this is a local physics kind of issue. It's not that we would expect that degenerate helium cores would behave differently in different parts of the universe. But that's another advantage of the tip of the red giant branch method, is that we're not having to worry about pulsating atmospheres and the fact that the metallicity of a star, a younger star will have a higher metallicity. So within a single galaxy, you could have spread in the period luminosity relation just as a consequence of evolution. All the stars at the tip of the red giant branch have the same luminosity set by the physics of the nuclear physics of the core. So I think, as we refine our measurements, of course, we could find differences that could become significant, but we do test for those things, and those they're not simply an assumption. We are actually measuring and comparing different galaxies, and within the uncertainties, they agree.
Yeah, so tip of the red giant stars, it appears that there is less uncertainty, less sort of things affecting the measurements. I was wondering, Wendy, I know that this is probably not the case. So the tension has been between C and B that seems to fit everything that we know, and that's showing 67. Local measurements show something above or close to 70. Is there some sort of a bias selection problem? I know that we are not really, we are just looking at about 24 samples, right? Could we just unfortunately picked up 24 observations that sort of give us the wrong data?
I think statistically, it's unlikely that it would be a 10% effect. You could imagine that at the couple percent effect, you're unlucky, and somehow the mean of your sample is biased in some way, but it can't explain the whole difference. I mean, the difference between 67 and 74 is 9%, and that just is statistically incredibly unlikely. So I don't think that will be the answer, but you could also imagine there could be several effects that, again, at the 1% level or 2% level, if we discover that, I think the other thing to be said is some of these effects are covariant, right? So if you're trying to measure Cepheids and correct for the presence of dust, you need 2 filters to do that, at least 2. It's preferable you have more than that to correct for the reddening because it changes the color of the star. You also need to correct for this metal abundance effect, which is also a function of, it affects the color of the star. And then you have to worry about the fact that you're in these crowded regions in the spiral galaxies, and the crowding goes up towards the center. There are more stars in the center. The density of stars is higher. The metal abundance is higher, and the reddening is higher. So all of those effects go in the same direction. So you, when you're trying to correct for those effects, if you make an error, say because you got the wrong luminosity of your star because of crowding, then you get the reddening wrong, then you get the metallicity wrong. So there's covariance there that I think we certainly don't understand at the 1% effect level. And I think that again is why James Webb is going to be so important, because the resolution of the telescope is almost 4 times what we can get with the infrared camera on Hubble, and so we'll see directly, are these stars being crowded? We'll have better sensitivity, so higher signal to noise in the measurements, be able to measure the metallicities directly for the first time, and answer some of these questions. What is the level of the systematic uncertainty? And at the end, I still am, part of me, hopeful we're going to learn something about new physics, because that would be really interesting. But I don't know what the answer will be yet until we make the measurements.
So are you encouraged by the fact that your measurements in the tip of the red giant branch is coming closer to the CMB expectation? Are the error bars sort of overlapping now or close to it?
Yeah, the error bars of the tip of the red giant branch method and CMB are overlapping, and I think had we not gone and measured the Cepheids as part of the key project, and the later measurements of Cepheids are giving the higher values of 73 or 74, we would be saying this is consistent with lambda CDM, the cosmological constant cold dark matter standard model, and wondering what are the systematics and the Cepheid distance scale? How is metallicity hurting you, and so on? But I think, and it's the first serious test of the Cepheid distance scale. That was the reason that we set out to do this, is knowing that there are systematic uncertainties in any measurement. You won't improve the accuracy of your measurement by doing it in the same way over and over and over, right? If we're still using the Cepheids and we have these issues with, say, metallicity or crowding, we could make the measurement hundreds of times, but we're still going to have the systematic uncertainty. And so we designed the tip of the red giant branch Hubble program specifically to measure the Hubble constant independent of the Cepheids. The tip of the red giant branch has its own set of systematics, which are smaller, as you have seen, and give us some sense of what is the overall systematic uncertainty. And this first test says, well, wait a minute, there's not apparently a 4 to 6 sigma effect with the tip of the red giant branch, as has been claimed for the Cepheids. And so even in the nearest galaxies, we are seeing differences, and that says there's some systematic effect, right? That's not new fundamental physics of the early universe. That's, these galaxies are at a single distance. They can only have one distance, and if the Cepheids and tip of the red giant branch are giving different answers, there's some systematic uncertainty in one or both, and we better understand that before we claim that there's new fundamental physics that's required.
The other possibility, of course, is H naught is not a constant. It's changing with time.
Well, it is changing with time, right? I mean, that's
Okay.
We see that with dark energy, right? As a function of redshift or time, the expansion rate of the universe does change. That's certainly the case. But locally, spatially here in our local neighborhood, which is what we're measuring with the expansion rate today, right? H naught means time at t equals 0. That's what we're measuring, and the cosmic microwave background measurements that require, so these are measurements being made at the surface of last scattering, and redshift of 1100, and then it's the model the cold dark matter lambda model that allows you to then infer what the expansion rate is today. But it certainly has been changing with time. We know that.
Okay, so the H naught we are measuring from CMB is actually H naught at time equal to 0. It's not H naught 380,000 years after the Big Bang.
Right. You have to have a model, right? So if you assume that lambda CDM is correct, then you can infer the expansion rate today. And so when you do that, and so, as I said, the fits to the fluctuations that are being measured in temperature and polarization, if you use a 6-parameter fit for a lambda CDM model, it's an exquisite fit to those data. You don't need any additional physics. And so what's happened is, and when you have that fit, then you can say, okay, what would the expansion then rate be today based on the lambda CDM model? And you get 67. So if the local measurements are correct, that would say something's missing from the lambda CDM model. That's where that impetus is coming from. So we better be right in the local universe to claim that there's this extraordinary new physics. And it's there have been many measurements now, so not just say Planck or WMAP, but also measurements from Chile and the South Pole, the ACT measurements and South Pole SPT measurements that are agreeing with the measurements from Planck, and also measurements of the matter density. So-called baryon acoustic oscillations give a value of about 67. And so, and it's not completely independent, the BAO measurements from the CMB measurements, because you need to calibrate the baryon acoustic standard ruler, as it were, and that's, you assume basic neutrino physics calibration coming from the microwave background. And so at this point, I would say it's an intriguing result. It is a possibility. If you think of it, we don't yet understand what the dark matter is. There's been no direct detection of dark matter, and yet most of the matter in the universe is dark, and about 1/3 of the composition of the universe is matter. About 2/3 is in this form of dark energy, this lambda proposed by Albert Einstein, cosmological constant, appears to be consistent with the standard model incorporates that. But we have no idea what the fundamental physics is that describes this dark energy. We have no theory right now that can explain it. So when you have a theory where you don't understand at its most basic level yet what the major constituents of the universe are, it is an absolutely reasonable hypothesis that there are missing things from that model. How would you test that? Well, you would measure the Hubble constant locally, and you would compare it with what you would infer from a lambda CDM model. And if there were no missing physics, those two should agree. And right now they don't. And the question is that a significant difference? And statistically, if it were only statistical uncertainties, which is part of what you were getting at before, it might be okay. But the question is, are there systematic uncertainties that could be plaguing the distances? And these are hard measurements to make, as we've been discussing. These are not, we don't have a ruler we can go in a lab and measure a dimension with high precision and accuracy. We're using objects, stars, that are complicated in many ways, and that could have real physical types of systematics. It's not that there are measurement errors, it's that there's something about the astrophysics that's missing from our understanding of the stars that we're using.
Yeah, and we need more samples. So that is where James Webb comes in, right? So, I mean, this is a project, I was looking at the history of James Webb. It's a project that has been going on for how many years? 25 years?
25, 26, yeah.
That's an amazing thing. And clearly it's a very complex project. So this is going to have sort of an exposed mirror Sort of how big is it? 6.5 meters. That's the latest, or 8 meters or
5
something?
meters, yeah, and it's made up of 18 different segments, so it's that have to be unfurled in space. So yeah, it is an incredible engineering project. It's
And what's the spectrum that it's really focused on?
It's a telescope that will focus on the infrared, and so from near infrared to far infrared, and there will be a little bit of optical that can be done, but the sensitivity in the optical is much lower. So it's optimized. The diffraction limit, I think, is 2.2 microns.
And so was it 6.5, the diameter of the lens?
Yeah.
And so it's a single 6.5 meter lens.
No. It's 18 segments that.
18 different segments. So it's
So
really difficult to launch that thing, right?
So when the James Webb was first being discussed, so this was I was involved, in fact, in some of the early discussions of JWST. There was a committee that was charged with coming up with the successor to Hubble. And our committee recommended, in fact, a 4-meter telescope because, well, for two reasons. One, the budget of a larger telescope we didn't think would be feasible. It did turn out to be a very expensive undertaking. And the other was that there was no launch vehicle that had a fairing that was large enough to have something that was a 6.5-meter mirror. And so when our committee came out with the report, the director at that time at NASA, science director Dan Golden, had said, "You're thinking too small. I mean, this is just you guys need to think bigger," was how he put it. And so the telescope became bigger. There were proposals to build a bigger telescope, and the way to solve the problem of being able to launch something with a mirror that large was to do it in segments, and there are 18 segments to the mirror.
So it sort of folds in, and then when it's up in space, it's sort of like an umbrella. It opens up. Is that the idea?
That's right. It unfolds like petals in a flower, and I encourage people to go look this up. If it and you will appreciate just how daring and exciting this project is. Because there are also these giant sun shields that protect the telescope and the instrument from the direct radiation from the sun. Those have to unfurl. There are a lot of moving parts to this telescope. And it will go into what we call an L2 orbit. So it's actually a solar orbit. It's not going to be orbiting the Earth the way that Hubble does. So it's not a serviceable facility in the way that we could take up new instruments on Hubble and then repair it when there was the problem with the focus. This thing will be 1.5 million kilometers away from the Earth. And it's a Earth trailing solar orbit, and all this unfurling has to happen, remotely.
This is going to be the most stressful launch for a lot of people.
I'm sure that's a fair characterization.
I understand that we set out with a budget of 5 billion. By the time we actually get it out there, it'll be about 10 billion. And as you say, unlike the Hubble, we can send somebody out there to fix it up if something goes wrong. And so it's sort of a binary outcome, isn't it?
It is. And of course, we can never say never, but there's no way at the moment of getting out there to fix something at L2. And so we just hope that it will work. And I think that this is not new technology. There's reason to be very, very optimistic that it will work, but it is binary, as you say. It has to work. And so, yeah, I do remember when first when Hubble was launched, and then we learned about the spherical aberration and the fact that telescope couldn't focus well. And then watching the refurbishment mission and the astronauts taking out these giant piano-sized instruments and replacing them, we were just glued to NASA television, waiting. We couldn't do the key project that we had been awarded time to do. There were a couple nearby galaxies that we got some early data on, but we wouldn't have been able to do the project if it hadn't been for the fact that the telescope could be refurbished in space.
So what's the technical reason for the L2 position? Why a solar orbit and why L2?
It's a nearly stable orbit. It's not quite stable. There has to be some station keeping, but it's pretty close. And so a lot of telescopes now, the microwave background telescopes, it's become a popular place to park telescopes. So you don't have to worry about the sun as much. We have to worry with Hubble. You can't observe all the time with Hubble in an Earth orbit. It's much more efficient in terms of telescope observing time to get out away from Earth orbit, low Earth orbit.
That's because the sun is not moving, right? Is that one of the fundamental reasons?
Yeah.
So is L2 sort of a band around the sun, or is it a sort of a singular position?
It's sort of like a little, a little circle essentially around. It's almost stable, as I said, but not quite. I mean, it's being perturbed, and you have to do a little bit of updating the position, but but not a lot is required. So the lifetime nominally is about 5 years, and the hope is that it will last for 10 years.
But we could put multiple things in L2, right?
Yeah.
Not just a single thing.
No, it's not a point.
Yeah, I'm pretty sure, as space junk fills up everything, I'm pretty sure L2 is going to get filled up at some point. And so James Webb has a specific lifespan, right? It has to use fuel, and at some point there is no. At some point it's going to die, I would think, right?
That's right. And if I recall correctly, or at least I think it used to be, and likely still is, that it's the goal is 5 years, but the hope is that it could last for 10. And with Hubble, we've just been incredibly lucky at how long. And of course, with the refurbishment, that's made it possible, because several of the gyros have gone, and and Hubble could be actually. With the opportunity to put new instruments, state-of-the-art instruments, it's just gotten better and better with time. But that's not a possibility for James Webb.
I know that you're going to use this extensively. So going back to these observations, especially the tip of the red giant star observations, how will James Webb, what additional accuracy or information do you expect to get from James Webb?
Yeah, well, these tip of the red giant branch stars actually emit more radiation in the infrared. They get brighter in the optical. They get fainter with wavelength, but they actually emit a lot of their radiation in the near infrared. So because they're brighter, we can observe them to greater distances. So the volume of space that we can measure the distances to galaxies increases, and so we can increase our sample size, decrease the statistical uncertainties, and that will help us a lot. Unfortunately for the Cepheids, because Cepheids are relatively blue stars, in terms of discovering Cepheids, it's best to do that where the amplitudes of the stars are largest, right? They're varying in their brightness, but in the infrared, the amplitudes are really small. So discovering new Cepheids is not going to be one of the things that James Webb will do well. Hubble has been the perfect Cepheid discovering machine because it's sensitive in the optical where the variations are largest. So it will help us in terms of measuring more accurate luminosities to the galaxies where we already have discovered Cepheids, but not as helpful as it will be for the tip of the red giant branch in terms of discovering new objects at greater distances.
But mathematically, if you can show that the tip of the red giant branch is less noisy, is there any reason to go on the Cepheid route anymore? I mean, isn't your methodology sort of surpassing the original idea?
I think ultimately the tip of the red giant branch is going to be what will become the best standard. I think having different so if we can show directly that there is a problem with either crowding or metallicity, in principle, we can correct for that. We will have better data and we will be able to see how we do. The other advantage, of course, of the tip of the red giant branch is you need only a single observation to get the measurement of the luminosity of the star. With the Cepheids, we need at least a dozen observations to measure the periods and to determine the period luminosity relation. So it's much more cost effective in terms of telescope time. Particularly that's important for James Webb because it takes a long time to move this telescope to a target. So that would be a very big challenge for JW to measure Cepheids with any kind of efficiency. It will be much more efficient with the tip of the red giant branch. But I agree. I think tip of the red giant branch hasn't been studied for as long as Cepheids, but as we continue to improve the calibration, it's going to be very hard to beat it in terms of ultimate accuracy because of the simplicity of the method.
Yeah, so I was just thinking, Wendy, is this automatable? So can we put in some AI sort of heuristics in there as James Webb look for stuff? If it finds a tip of the red giant branch star, it just has to take one measurement, right? So it could almost sort of collect this data in an automated way, couldn't it?
So I'd like to understand better how it would have. So you have to. So we have, of course, programs now that go into our galaxy data set and measure the luminosities and then the colors, the temperatures of the stars, and then it's not as if James Webb is going to be surveying the whole sky, right? These are pointed observations. And so we need to tell the telescope where to point. Here's a galaxy, right? We don't have tip of the red giant branch stars floating around. And so I don't, I'd be interested to hear if people have ideas about where AI could be helpful in this specific context. It would be really interesting to hear.
Yeah.
But,
I was just thinking, I don't know anything about this. I was just thinking, since James Webb is a multi-purpose project, it's going to take a lot of measurements. But if there is some sort of a algorithm in there that says, as you take measurements, if you find one of these things, just take a photograph, sort of thing.
So one of the areas where we put a lot of attention is to ensure that we're making these measurements in the halos of galaxies, the outer regions. So we don't want to be anywhere near the disk where we have all these potential systematic effects like the dust and crowding and so on. So we have, in some cases, tens of thousands of these stars in the halo. We know where to look. We essentially set our algorithms measuring these luminosities automatically, right? That it's and then we look for this very precise edge to the luminosity function of the halo stars. So as I said, if anybody had ideas about where this could be useful, I'm not an expert in AI, and I don't immediately see where it would come in, but I'd sure be interested to hear.
It sounds like you will ultimately get a large data set if James Webb is functional and doing its observations.
Don't say if, please. When, yes.
When James Webb, I have to be optimistic here, when James Webb is functional and taking all this measurements, so there will be a large data set of tip of the red giant stars. And that should settle the score, I would think, right? I mean, if you have, what would you say the number is? Let's say you have 1,000 data points. Don't you think at that point you have, sort of sufficient constraint on where you end up?
So I think this really will allow us to say, is this real or not? Whether we get to 1% accuracy because of effects that, again, unknown systematics. It's unfortunate, but not surprising that it's usually something that you're not even thinking about that comes to get you in the end. And so when we were trying to solve the factor of 2 debate with the Hubble Constant and Cepheids, there were things nobody had corrected for reddening before that time, or slightly before. When we got CCDs on the ground, we started to investigate this. Nobody had paid attention to the metallicity issue. And it wasn't possible to make those measurements because when you had a factor of 2 uncertainty, you couldn't, it was in the noise. And then as our measurements improve to the 10% level, we could measure 15% effects or and I think as we push down now to 1 or 2% where we want to be, there are going to be other things that we will be able to measure for the first time that right now we have no hope of doing. So again, it comes down to systematics, but at least we'd be able to isolate those kinds of effects once the data get more accurate, and you know, other effects will poke out. Now, we won't have 1,000 galaxies, right? We might have 1,000 stars per galaxy, but we're not going to get to the point of having 1,000 galaxies. So, but we will get to the point where I think the statistical uncertainties will be very small, and again, it's up to us to reduce the systematic effects. But the increase in the sensitivity, the wavelength coverage, and the resolution will allow us, and the different techniques will allow us to do that. Now, if we have a disagreement, so you know, your earlier question, will we need the Cepheids? We can't predict what will happen, but if the Cepheids, the tip of the red giant branch, ultimately gravitational wave sirens, which I think is a method of the future, there's only one object right now, but if we had 3 or 4 measurements that all had quoted precisions and accuracies at the 1 to 2% level, I think we would be confident that we had a robust overall measurement. And that's what we did in the key project. We had 5 different methods, secondary methods, and then we also used the tip of the red giant branch to test the Cepheids and auroral Lyrae stars. And so we could get an overall estimate of the systematic effects. If you have only one measurement, which coming back to why I said we started to do the tip of the red giant branch, is with Cepheids we'll never know alone. But if we do get convergence, I think we will have confidence. If we don't, we will continue to learn, and we just don't know yet where it will land.
Yeah, that's what makes it feel really exciting. So in conclusion, I want you to speculate a little bit. For general public, think about cosmology. It seems like we have a long way to go. We have dark matter, we have dark energy. That's 95% of the universe. We still don't know a lot about it. We have these measurement errors that we see from different methodologies that gives us some clues as to something might be missing. We haven't really been able to bring gravity into a unified theory. So where do you think we will be, let's say 10, 15 years into the future?
I would hope 10, 15 years into the future, we will have settled these issues now. There are other hints that there may be cracks in the cosmological model, but they're at maybe the 2 sigma level. There are no claims of 4 to 6 sigma level effects. But there are so many things coming on the horizon. There are the extremely large telescopes like the Giant Magellan and the European Telescope and the TMT and so on. And those will allow us, again, to open up new frontiers and really make progress, I think, on questions about dark matter and dark energy. And the Gaia European satellite, the Parallax satellite, those measurements are getting better and better with time, and those will continue to improve. We've been discussing James Webb, and that will get better. I think what we really need is a theoretical breakthrough. We're not going to understand what the dark energy is without some new idea that we don't have at the moment. I still find myself wondering, could we, and it might not be 10 or 15 years from now, but 50 years or 100 years, if we look back, are we asking the right questions? Maybe we're not. Maybe we've taken a slight detour and our picture of the universe will be very different. But the way we will, I think, ultimately determine that is by continuing to get better and better data, and new ideas will surface that things may lock into place in a way that we're at the edge now of our understanding, which always makes it an interesting field. And it's, the juxtaposition of theoretical ideas and new data continually confronting each other is where you make progress. But we, as you say, there is a lot we don't understand right now, and the prospects of learning even more, which just makes it an incredibly exciting time to be working in the field. And if you have young listeners, there's so much to do. And figure out what the dark matter, discover a dark matter particle, tell us what the dark energy is fundamentally from a theoretical physics point of view. Nobel Prize is waiting for some young person somewhere.
Absolutely, yeah. I mean, the scary thing for me is, as a thought experiment, where would humanity be if Newton, Maxwell, Einstein, Hubble, just to mention a few, didn't show up at the right time points? We would be in a different trajectory altogether, right? And so we don't know. We don't know which trajectory we are moving on in the absence of, as you say, that theoretical genius not showing up or showing up. We don't know.
Yeah, and there are different types of problems too, and different types of people, right? I think you're right. There are certain times. Einstein, if he hadn't shown up when he did, there was nothing in the air at that time that suggested general relativity, and that was he showed up at a time where it really had an impact on our understanding of the cosmos. Other types of results, things were in the air and will eventually be discovered, but I think there are certain geniuses who have been at the right place at the right time that have really changed the way we look at the world we live in, and that will continue. But that might not happen for a while. Some things Einstein didn't have, in his search for a unified theory, he didn't have the building blocks that were needed to do that. So sometimes the timing is just not right.
And we don't know the counterfactuals. So if Einstein too showed up in 1980, we would have solved all this problems by now, potentially, right? But that experiment hasn't been run yet. So yeah, so there's a sort of discontinuous knowledge that comes to us, right? And then we take that discontinuity and we try to push that forward incrementally. But if that discontinuity doesn't happen, it takes a long time.
Yeah, and it can't decline. So, some scientific fields dry up for a while, and then, it's either new technology or some brilliant insight of a person who comes literally from left field with a different way of looking at the world. So, and when you're in the midst of it, you don't know where you are at a given time. So.
Excellent. Yeah, I know that you have to go. This has been great, Wendy. Thanks so much for spending time with me and coming back on the show.
Enjoy our discussions. Thanks for having me.
Thank you.
Okay, bye-bye.